Okay, so I previously was just talking about really the spectrum, acids, bases, or neutral. Really, those are the three options, right? Well, one of the things we can use then is qualitative data, right? If you're doing an experiment, qualitative data would be something like it turns litmus red. Makes sense? Or it reacts with zinc. But we should also hopefully be able to do quantitative data. And you guys probably have a little bit of familiarity with this. If I were to give you a pH scale, you guys know this, right? A pH of 7 is neutral, whereas if it's above 7, it means that it's a base. And if it's below 7, it means that it's an acid. This topic here is about how to reconcile what we just talked about acids, bases, and neutrals, but how to also get ourselves a quantitative measurement to go with them. Does that make sense? So a quick little bit of review then. What we just talked about then is how is something an acid? Well, something is an acid is if it produces H3O+. And something is a base if it produces OH-. Well, somebody really clever figured out here. I have a way to quantify these. Why don't we find the concentration of the products, not the concentration of the initial thing, right? Like, how do I put this here? I don't care about the concentration of this. This is not what I care about the concentration of. But if this guy is an acid, this is the reason why it's an acid. So why don't we find this guy's concentration? And that will allow us to numerically add a number to things. Does that make sense? It's actually quite brilliant. It's very clever. And so what we've discovered then is that if something is a neutral solution, it has an acid content of exactly 1 times 10 to the 7 moles per liter. And for right now, just hold on to that number. I'm going to explain where it came from in a bit. But if it's a neutral solution, we've discovered that it has an acid concentration of that right there. Actually, no, I'm going to do this right now. Neutral solutions, why should they have acid in them? What's a neutral solution? Which produces? Water, yeah. You guys remember how water is the one item that is both an acid and a base? The reason why is that water actually has the ability to break apart into a hydronium and a hydroxide. Remember talking about this last day? But it doesn't happen very often. We've actually discovered it happens 2 parts per billion. 2 parts per billion. I want to write that out here. If it happens 2 times in a billion, it means if you had 1 billion molecules, one of them would be a hydronium, and one of them would be a hydroxide if you had water. And then immediately those two would probably recombine to form water, another one would break apart. And then those would recombine, and another one would break apart. Makes sense. But if you agree that then if it's 2 parts per billion, then this is really 1 in a billion, whatever, that's a billion, let's say. And that's 1 in a billion. Well, it means then that water, even though water, you believe water should be neutral, water actually has some acid molecules in it. It also has an equal number of base molecules in it. That makes sense? And based on that logic, 1 part per billion, this is one part per billion of this, and 1 part per billion of this, actually correlates to that concentration right there. So even though you'd think that water should not have acid in it, it actually does. It has a very, very, very small amount of it. I mean, how big is 1 times 10 to the minus 7? 0.00000001. Right, like, is that concentrated? Not even remotely close. But hopefully you can understand how where this came from here, is that because 1 in a billion water molecules makes acid and base, then actually neutral solutions actually have a concentration of acid. Well, once we got the concentration of acid molecules in water, which is neutral, then it was really simple. If you have more acid molecules than what water is supposed to have, then you're an acid. Seems logical, right? And if you have less H3O molecules than what water has, then you're a base. So let me walk you through that process one more time. We've discovered that water actually has the ability to ionize into H3O and OH-. Very rarely, 2 in a billion. But it happens on rare occasion. Well, if you're okay and comfortable with the idea that water can actually be both an acid and a base, which you've seen at some point before, right? Water is the product of an acid and a base. Then it means that all water molecules have a little bit of acid content in them and a little bit of base content. So that little bit of acid content, 1 in a billion, actually corresponds to this concentration right here, as cool as it is. Well, then if we consider this to be neutral, then anything that has more acid in it than water does is an acid. And anything that has less hydronium in it would then be a base. And now we can start to numerically rank these things. Now this is actually really cool that we're doing this at the exact same time, but in math, you guys that are in grade 12, you're going to start talking about something called a logarithm. You guys in grade 11, sorry, you'll cover it next year, but we're going to use logarithms in chemistry to help us out with numbers, because here's one of the problems. These numbers here are so small that it's really not fun to work with like 0.000000157 moles per liter. Like, that's such a small concentration that it gets really annoying to do this every single time. But logarithms were developed in math to try to make it so that we take really small numbers and turn them through an operation into some more reasonable numbers. And so later on today, I'm going to show you guys a formula that we use to convert these small concentrations into something more normal. I'm going to go through my notes here. Okay, here's what I was just talking about. 2 water molecules turn into a hydronium and a hydroxide. 2 parts per billion gives you this concentration. I think I already said this. So, 1909 then. This is really like after everything we've talked about. Like up to Arrhenius, we're now at the point where we finally discovered the nucleus. Rutherford discovered the nucleus 2 years earlier.
Alexa Cooper, Amy Craig, and Brandon Creighton. Please come to the office.
Soren Sorensen, which is like the coolest name ever, Soren Sorensen, introduces this idea called powers of hydrogen. And that's actually where the name pH comes from. P, power, H, hydrogen. Powers of hydrogen, that's where pH comes from. And he basically says this statement right here, which is way too confusing, so let me just show you what it really means on paper. Let's say that this number right here is how much hydronium ion concentration you have. 1.0 times 10 to the minus 2, which is 0.01 moles per liter. That's how much acid you have. Is this more acidic than water? Where was water again? 1 times 10 to the minus 7, right? Well, this is clearly bigger. It's still small, right? It's still a small number, but it's bigger. Well, what he came up with is the idea of, okay, I don't want to write this number here. So he used exponents and logarithms and said, let's just give it a pH value. And this guy's pH value ends up being 2. Which, if you have no experience with logarithms and exponents, you're like, how the heck did you turn this number into this one right here? But it has everything to do with this number right here. See how it's times 10 to the minus 2? Well, if it's times 10 to the minus 2, then we give it a pH of 2. Okay, let's talk about this for a second here. I'm going to go back a slide. What was the concentration? Sorry, this is so small here. What was the concentration up here of water? Times 10 to the minus 7. What pH do we give water? That makes sense? That's why. Because 1 times 10 to the minus 7 is 0.000000123, like something like that. I might have missed a 0, right? It's annoying to try to write this number every single time. But if we put it on a pH scale, then really what a pH scale does, it tells you how many zeros you have in front of a decimal place. Okay? If you have 1 times 10 to the minus 7, you have 7 zeros in front. He said, let's just call that a pH of 7. Well, then what happens if you had 1 times 10 to the minus 3? Is times 10 to the minus 3 more acidic or less acidic than water? It's more acidic. I know that 3 is actually a smaller number than 7, but it means that you only have a couple of zeros in front. So this is now more acidic. Well, what's the pH of this thing now? 3. It actually helps to explain another really common confusion. Why are the low numbers acids? Well, the reason why the low numbers are acids is because they have fewer decimal places in front of their concentration values. And if they have fewer zeros, they're actually bigger numbers. And if they're bigger numbers, they're actually more acidic. Let's say that one more time. Why are low pHs acidic? A low pH actually has fewer 0 decimals in your number, right? So if you have a pH of 3, now let's do a different one here. Well, let me go back to the one I have here. Let's just use the one I have. If you have a pH of 2, right here, it means that it's 1.0 times 10 to the minus 2, which is really 0.01. If you had a pH of, say, 13, a pH of 13 is a base, right? If I were to write out its concentration, it's 0. Something like that, right? Well, does this have a high acid concentration? Not even close. I mean, this is well below what water's concentration would be. So that explains why a pH of 13 now is a base. So here's the new formula I need to introduce you to. It's actually really easy. If you want to find a concentration, take 10 and go to the power of a pH. That's it. So let's try an example. I actually even have one sitting here. What if you have a pH of 3.75? So right off the bat, pH of 3.75, is that an acid or a base? It's an acid. We know that because it's lower than 7, right? But now we can quantify this just using this formula here. All I need you to do is go 10 to the power of minus 3.75. So if you don't have a calculator nearby, let me show you how that looks. Clever graph. All you've got to do is go 10 to the power of negative 3.75. Yes? Well, okay, so what ends up changing here is that when you get your answer, say you get 1.778 times 10 to the minus 4, the reason why is that previously all of the pHs I was using were whole numbers. What if the pH isn't a whole number, though? See how this is 3.75? Okay, well, 3.75 is pretty close to 4, let's say, right? Can you see now how the exponent here is 4? But the difference here being is this was not the number like 1 right on the dot. There were some decimals there. You kind of see how that doesn't jive perfectly. If it literally is 1.0, like exactly 1 right on the dot, then the pH is a nice round even number. What are the chances that your concentration was 1.0 repeated? Right? What if it's 1.5 or 1.7? But hopefully you can kind of see the relationship here. This pH of, let's call it 4, correlates with a exponential value of basically 4. Let's try another one. What if I were to give you a pH of 11.57? First of all, before you even type anything in, acid or base? Definitely base, right? Okay, well, if you go 10 to the power of negative 11.57, it will then give you a concentration of 2.69 times 10 to the minus 12 moles per liter. Is that highly concentrated? Not even close. Clearly lower than what water does. And keep in mind, water only does this 2 times in a billion, right? Will you find a random particle of acid in a base? Actually, yeah, you will. You'll actually find random particles of H3O plus in bases, but like they are so infrequent, so impossible to find, that this is well below what even water does. And then hopefully you can see the relationship. Here, this pH was basically 12. What's your exponent? So, can you guys cover it? This is actually what you guys are going to work on in Math 30-1-2. And then for you guys in grade 11, we'll get to it. But we're focusing on exponent now. So, little side note then. You guys have probably been told at some point that the scale for pH goes from 1 to 14. It's actually a lie. The only reason why we go from 1 to 14 is because dab smack in the middle of that is number 7, which is for water. But it's actually possible to have even more dilute solutions or even more concentrated solutions. It's actually possible to have a negative pH. Oh my goodness, you guys are amazing. Keep it on. Alright, so sweet guys. I'm so impressed. We'll make sure we're really careful with that. Thank you so much. You guys see that? That's the box we use. That's beautiful. Okay, anyways. Here's what I need you guys to know. The pH scale can actually go as low as -1. Which seems really weird, but let me talk about this for a second here. You guys remember how on your data sheet we had a breaking point of things that are slightly soluble and that are very soluble? What was that breaking point? 0.1. Watch this. What if I were to... I have to show you the formula to do this. Hang on. Where do I have that? Okay, hang on. Can I come back to this thought? Sorry, I'm scattered here. if I were to give you a pH, there's an easy way to find the concentration. If I give you the pH, your concentration was 10 to the minus pH. But I need to show you the way that you go the other way. What if I give you a concentration and I want you to find me a pH? So let me show you that formula and I want to come back to the slide. So here's that formula here. This uses logarithms, which we'll show you more of in math at some point. Here's the other formula here. If you want to find a pH, you take the negative logarithm of your concentration. It's not as hard as you think it is, I promise. It's actually really easy. What is the concentration of the acid in water? Times 10 to the minus, okay, watch this. Negative log 1.0 times 10 to the power of negative 7. If you do this, it will give you the pH of 7. It's over here by number 7. Here's what a logarithm does. A logarithm takes a very, very, very small or big number, and it basically tells you how many powers it has. Let me show you another one here. If I took the negative logarithm of 0.00005, let's try this number here. Count my zeros up. I basically have 1, 2, 3, 4, 5, 6 zeros in front. If I were to then calculate the logarithm, it'll give me an answer of basically 6. And the reason why is a logarithm basically tells you the order of magnitude. Okay? The more zeros you have, the bigger the number. See how this one had 1, 2, 3, 4, 5, 6 zeros? That's why it's got a pH of 6. If I were to do the negative logarithm of 0. Okay, let's take a guess as to what this pH would be. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm going to guess this is going to be about 15, a pH of. Does that make sense? Just based on the magnitude of this. See how that works? So a logarithm is a really clever mathematical tool that will allow you to tell you how many decimal places you have. So if I were to ask you to find the log of 0.1, this is where I want it to go now. Remember how when we were talking about our break-even point? What's the log of 0.1? Don't press enter if you haven't yet. How many decimal places are in front of this guy right here? Don't count this one right here. How many zeros are like these ones right here? I actually don't have any. So now this one right here, basically that you just count this 0 right here. But what if you had a concentration that's even higher than that? What if your concentration was 1 mole per liter? You can actually get a pH of 0. Do you guys remember what the strongest, most concentrated acid I had in my lab was? How concentrated it can get? Yeah, I have sulfuric acid at 18 moles per liter. If I were to take the negative log of 18 moles per liter, you can actually get a negative pH. So if I can go back a slide, because I know I jumped around a little bit here. The point I want to make here is that most pH scales go from 1 to 14. And when you guys are originally learning it, it's because 7's right in the middle, and that hopefully helps make sense. But really what the pH scale is telling you is how many zeros you have in front of your concentration of acid. The more zeros you have, the less concentrated it is, therefore the higher the pH. The fewer zeros you have, the lower the number. It's actually possible to have a pH of like -1. So I need you guys to know 2 formulas. Here's one formula. And then on this slide right here is the second one. So let me try a couple examples and then we'll move on. Here's another one here. Let's say that I give you a solution with a hydronium ion concentration of 3.07 times 10 to the minus 11 moles per liter. Stop there. Where's that break-even point between acid and base? Times 10 to the minus 7. Okay. Is this going to have more acidic content than water or less? Less. And not just less, but less by 5 orders of magnitude. 4 orders of magnitude, right? Because water's to the power of -7. So then 8, 9, 10, 11. Like, it's not just that it's 4 times less acidic. It's like, it's actually 10,000 times less acidic. Because each 0 that you add is 10 times more. You get what I'm saying here? If this were times 10 to the minus 7, it would be 0.1, 2, 3, 4, 5, 6, 7. Okay. But this one's to the minus 11, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How does this number here compare to this number here? There are 4 extra zeros from this number to this number right here, which means that it's not actually 4 times weaker, it's 4 tens less weaker. So really, it's 10 times 10 times 10 times 10. It's actually 10,000 times weaker. Does that make sense? That's how exponents and logarithms are going to work in this section. Long story short, here's what I need you guys to be able to recognize. Look, this minus 11 right here, more or less is referring to how many zeros you have in front of this number here. And because there's minus 11, when you actually calculate the pH, ta-da! Okay, now the pH won't exactly be 11, but that's because this number right here wasn't 1.00. If this number here was exactly 1, then your pH would have been 11. Since this number right here was slightly bigger than 1, let's do this one more time. Since this number right here is slightly bigger than 1, it's slightly more acidic than 11. Isn't 10.5 slightly more acidic than 11? Here, let me do 2 more examples and then we'll move on. So here's what I want you to do. Find the pH of a solution which has a concentration of, let's say, 1.75 times 10 to the minus 4. And then I want you to find the hydronium amount if the pH is 8.57. You actually don't need a calculator to guess a rough estimate on this. If you understand what I'm trying to tell you here about exponents and logarithms, you can actually guesstimate it.
Really instructions to the following students. Please come to the office. Harris Dion, Drake Featherstone, Hayes Gillingham, Nicole Goodrider, Akira Glidden. Please come to the office.
Okay. Without typing it in, I can estimate the pH of this guy right here is going to be roughly 4. I actually think it's going to be less than 4. I think it's going to be 3 point something. And here's the reason why I think it's going to be 3 point something. If this was 1.00 times 10 to the 4, it pH should be 4. But this is 1.75, which is slightly more acidic. How does pHs work for slightly more acidic? It actually means that you have to make the number slightly smaller. So I'm going to guesstimate the pH of this is going to be 3.8 or 9. So then to test it, to find that pH, you go negative log of 1.75 times 10 to the power of negative 4. That's pretty close. 3.8, let's call it. That logic makes sense? This 4 up here means the pH would be 4. If this was 1 right on the dot. It's not 1 right on the dot. So we have a slightly more concentrated solution because this number is kind of bigger than 1. So we have a slightly more acidic solution than a pH of 4. But more acidic on the pH scale actually means a lower number. So that's why my lower number was 3.76. Is it able to follow that? Okay, let me try the other one here. What if I give you the concentration if the pH is 8.57? Before I even move, I'm fairly confident when I'm done, my exponent is going to be times 10 to the minus like 8, maybe 9, somewhere up there. All you've got to do is go 10 to the power of negative, and then it's 8.57. Okay, so this is 2.69 times 10 to the minus 9. Let me walk through why this makes sense again. If this is a 9 right here, this means the pH would be 9, which is a base. But this was actually 2.69, not 1.00. So hopefully you can agree that this is actually slightly more acidic than a 9, because this number is slightly higher than 1 right on the dot. So what does that mean on the pH scale, though? Slightly more acidic means that the pH is actually a little bit lower than it was originally. If you can follow that train of thought, that's awesome. If not, all I need to know how to do is use these two formulas. Okay, we're almost done. Now, there's one more thing I need you guys to know, is that there's actually not just a pH scale. pH stands for the powers of hydrogen. But there's also something known as a pOH scale, which is just the powers of hydroxide. I want to use the same logic that I just walked you through, only now I want to flip it for bases. Okay? Remember how water has the ability to, two of them, break up into H3O plus and OH minus? We've only been focusing on the H3O plus. But water is a base still. Right? Water is an acid and a base, very, very, very dilute quantities, but the exact same thing. That same logic can actually apply to bases. And I'm going to go back to my very first slide here again, which is a disaster. And I just want to walk you through one more idea here. So if I erase this, fix it. What's up?
You're always playing in here. You ever teach anything?
No.
I'm away this afternoon, so go ahead without me in Sunday.
Okay. You're not here at 11?
That's about when I'm leaving.
Okay. So okay. I'll give you a principal's address.
You can.
Okay.
If I'm here, I can do something. But
Okay. We just wanted to give you 5 minutes of principal-y type time to.
yeah, I can do it if I'm here, but
Okay.
plan to go on without me.
Okay. Apparently, I can't fix the slide. Can you guys see how it was supposed to be equals, greater than, or less than? Okay. If we were to flip this and talk about bases, I'm sorry that it's so small. I don't seem to be able to fix this. But if we were to talk about bases, a pOH is related to your hydroxide concentration. The only thing that would change then, if you can imagine this, is that okay, your hydroxide concentration, when it's neutral, is still going to be 10 to the minus 7, because you have equal amounts of acid and base. But if something is acidic, you're actually going to have less hydroxide, and if something is basic, you would actually have more hydroxide. We can actually do the exact same thing for a base, only literally we flip everything. Give me a sec. This is actually, it's so confusing at first, and I promise you this is one of the easiest things we do. Okay, let me use this table here. I think I can explain it like this. If you have a high pH, it means you have a very low amount of hydronium, which means you're a base. But we could also talk about what's called the pOH scale. The only difference here is that they're like complete flips. Look at this. If you have a pOH of 14, a pH of 14, you have a pOH of 0. If you had a pH of 10, you'd have a pOH of 4. 7 gives 7. 3 gives 11. What do you notice about these numbers here? They always add up to? Okay, here's the reason why. For every one acid that water ionizes to make, it also does one base with it. And so basically these scales are exact inverses and are flipped of each other. As H3O gets more concentrated, you actually have lower pHs. As H3O gets more concentrated, you actually have a higher pOH. Long story short, if I want you to calculate a pOH, all you've got to do is take 14 and subtract the pH, and you have what's known as a pOH. Randomly, Sorensen decided to go with the powers of hydrogen scale. He just picked hydrogen to go with. But in theory, we can have the exact same scale with hydroxide. All you have to do is just flip it. If you look, you have a question here. Because Sorensen only picked hydrogen to go with, but in theory, he had a 50-50 shot. He could have gone with acids as a scale, but in theory, he could have gone with bases. And so we almost always just go with pH. Right? But all I'm trying to show you here is that in theory, we could talk about pOH, and the only difference is if I give you a pH of 13, it means the pOH is 1. So, your question's valid. Why? We don't ever use the pOH scale. Like, no one in any reasonable line of work I can think of talks about pOH. It's not purposeful. But if you get the idea that we could have talked about bases rather than acids the whole time, then you just have to flip your line of thinking. So, hypothetically, I give you a pOH of 3. Acid or base? Base. Now, a pH of 3 would be an acid. but a pOH of 3 is actually not a base. Right? That's all you gotta do. You just gotta flip it in your mind. The key is that they're both even at 7s. Okay, so let me do a couple of examples here, and then we'll call it a day. I promise, guys, although this sometimes seems confusing at first, mathematically, it's literally the easiest thing in the world. You need to know 2 formulas. One of them is that your pH is equal to the negative log of your H3O plus, and that your H3O plus is equal to 10 to the minus pH. That's it. You just need to know these 2 formulas. However, maybe this answers your question better, Rebecca. What if we don't want to know about acids? What if we don't want to know about H3O plus? What if we want to know about bases? Literally take the exact same formulas you see there and just change them for OH and pOH. That's all. So here's my question. What's the hydroxide ion concentration? Or sorry, what's the pOH if we have a hydroxide ion concentration of this right here? I'm going to take a guess on it. I think it's going to be about 2. The reason why I think it's going to be about 2 is because of those 2 zeros right there. That's my guess. So, now I know this is hydroxide, but shouldn't the same first formula work here? Literally, to find a pOH, just negative log the OH concentration. So if I negative log 0.0036, okay, I have a pOH of 2.44. Okay, a pH of 2.044. Acid or base? A low pH is a base. Follow-up question then. What if I wanted you to give me the pH? Because, Rebecca, maybe this answers your question better now. We don't usually use a pOH scale. A pOH scale sounds dumb. But here's how this would work. If I give you hydroxide, hydroxide gives you pOH. How do you get from pH to pOH? What do the numbers have to add to? 14. So a pOH of 2.44 is dumb. But isn't it pretty easy to tell you that the pH is going to be 11.56? You guys get what I did there? In my head, I just figured out what's it need to be to add up to 14. So I think maybe this explains your question better. The reason why we would use a pOH scale is we would never use this. This number here is stupid. But if I give you a hydroxide concentration, hydroxide can give you pOH, and then you can flip it to pH real fast. That's it. Does that help answer your question? Let me try another one. How many times bigger is the concentration of hydronium ions in a solution pH of 3 than pH of 6? And we'll call it a day here. Sorry, I went longer than I wanted to. I want to make sure I did a good job of teaching this today. How do I calculate my hydronium ion concentration? Well, the formula for this is 10 to the minus pH. So one of them is 10 to the minus 3. I mean, literally, this is going to make the number 0.001 moles per liter. What happens if it's 10 to the minus 6? Well, if it's 10 to the minus 6, then it's 0. Moles per liter. I already kind of alluded to this a bit. This one's right. I want to make sure I didn't script the zeros. 10 to the power of negative 6. Yeah, 1 times 10 to the minus 6. 1, 2, 3, 4, 5, 6. Yeah, I did it right. How many times, actually, let me start with one here. Which number is the bigger number? Is this or this the bigger number? Top or bottom? Is this number or this number a bigger number? The top one. Which explains why a pH of 3 is actually more acidic than a pH of 6. Does that logic make sense? The question is, how many times bigger is one over the other? The answer is 1,000. Yeah, if you were to take 0.001 and divide it by 0.000001, It's 1,000 times bigger. Here's the reason why. Each one of those extra zeros is 10. Right? Like, in terms of how these numbers work, each of these zeros is a factor of 10. So by having an extra 0, an extra 0, an extra 0, really, that made it 1,000 times smaller. Right? 10 times 10 times 10 is 1,000. Who feels confused? All right, let me give you a quick summary here. I don't mean for this to be super confusing, because really, all you need, I promise you, is practice. There are literally like 2 things you need to be able to do. If I give you a pH, 10 to the minus pH gives you a concentration. Okay. If I give you a concentration, negative log the concentration, it gives you the pH. Only the reason I show you a pOH scale is, what if I don't give you a concentration of acidic stuff? What if I give you the concentration of basic stuff? Well, then still use the same formula like normal, find a quote-unquote pOH, and then just subtract it from 14. Does that sound good? So it's one of those things where I promise you, after you've practiced it like 5 times, you'll probably get it. After that, if it internally makes sense, you don't need a ton of practice on it. But like, you do want to try it sometimes. So why don't I call it a day here, because I went longer than I wanted. Tomorrow, let's try a lab, and then I believe, what is Friday, work day? I hope so too. I do not remember though.
I'm gonna check real fast here.
Okay, let's do a work day on Friday. All right, let me alter the schedule a little bit. We have time. Why don't we? I still want to do the lab tomorrow because I think that'll help. But let's not make anything do in chemistry till Friday, other than the previous lab. Let's take this lesson on indicators and let's pull it to next week. Maybe what I'll do is I will shuffle everything so that we would maybe do. Why don't we write quiz 2 on this Monday here? Take a work day on Tuesday and do the unit test on the Wednesday. We'll push some stuff back. Does that work? Okay. No, next Wednesday. This weekend. No, just Monday. Okay, sorry that went longer than I wanted to, but I hope I made sense. If I didn't make sense, make sure you ask me, okay?